Gas chromatography, or GC, is a technique that is used to separate, detect, and quantify small volatile compounds in the gas phase. In GC, liquid samples are vaporized, then carried by an inert gas through a long, thin column. Analytes are separated based on their chemical affinity with a coating on the inside of the column. Because GC requires analytes that are vaporized to the gas phase, the instrument is ideally suited for volatile, nonpolar chemicals less than 1,000 Daltons in mass. For larger, aqueous, or polar molecules that are difficult to vaporize, liquid chromatography is a useful alternative. This video will introduce the basics of gas chromatography and illustrate the steps required to analyze the chemical species in a non-aqueous mixture using a sample gas chromatograph. The GC instrument has 5 essential components. First, an injection port is used to introduce the sample into the instrument. Next, a heating chamber vaporizes the sample and mixes it with an inert gas. The inert gas, such as helium or nitrogen, carries the vaporized sample through the system. Combined, the carrier gas and sample make up the mobile phase. Next, the mobile phase enters the heated column, separating the analytes as they flow through. Lastly, a detector records the gases as they exit the column or elute and sends data to a computer for analysis. The most critical component of the instrument is the column. The column is a capillary with a stationary phase matrix coating the inner walls. Alternatively, columns can be packed with matrix-coated beads. The stationary phase is usually modified polydimethylsiloxane, which is ideal for resolving nonpolar molecules. Its separation properties are refined by adding 5 to 10% phenyl, cyanopropyl, or trifluoropropyl groups. Analytes with low chemical affinity for the stationary phase move quickly through the column, while molecules with high affinity are slowed as they adsorb to the column walls. The length of time a compound spends inside the column is called its retention time, or RT, and allows compounds to be identified. The detector sits at the end of the column and records gases as they elute. Flame ionization detection, or FID, is widely used because it senses carbon ions, allowing it to detect virtually any organic compound. In FID, analytes combust in a hydrogen-air flame as they exit the column, producing carbon ions that induce a current in nearby electrodes. The current is directly proportional to the carbon mass, thus the concentration of the compound can be determined. The final result is a chromatogram, which is a plot of FID signal versus time, showing each eluted component as they exit the column. Ideally, each peak will have a symmetrical Gaussian shape. Asymmetrical features, such as peak tailing and peak fronting, can be due to overloading, injection problems, or the presence of functional groups that stick to the column, such as carboxylic acids. Now that the principles of gas chromatography have been discussed, let's take a look at how to carry out and analyze a gas chromatography analysis in the laboratory. Before running an experiment, turn on the helium gas tank. Open the software on the computer, then bake out the column to remove any potential contaminants. Set the oven to a high temperature, typically 250 degrees or above, and bake the column for at least 30 minutes. Next, adjust the auto sampler settings. Set the number of pre- and post-run rinses to clean the column between samples. Use a sample volume of 1 microliter and set the split ratio setting to program the instrument to accept only a fraction of the input. Adjust the flow rate of the carrier gas and use established settings or trial and error to find the ideal pressure. Now, enter the temperature settings for the experiment. For an isothermal run, enter the temperature and the time for the separation. Alternatively, for a temperature gradient, enter the starting temperature and hold time, the ending temperature and hold time, and the ramp speed in degrees per minute. Set the time for the column to cool between runs for either a gradient or isothermal run. Finally, set the sampling rate and the detector temperature. The detector must always be hotter than the column to prevent condensation. After all the settings are programmed, save the methods file. Activate the detector by opening the hydrogen tank valve and ignite the flame of the FID. The instrument is now ready for sample analysis. To run the sample on the GC, first, fill a vial with a wash solvent, such as acetonitrile or methanol. Prepare the sample, being certain to use glass syringes and glass vials, as plastic residues can contaminate the GC. Now add the prepared sample to the vial with a glass pipette. Fill the vial at least halfway so that the auto-sampler syringe will be fully submerged. Then, load the wash and sample vials into the auto-sampler rack. Before running the sample, zero the baseline of the chromatogram on the computer software. Data can be collected either as a single run or using a batch table for multiple runs. Press Start to run the sample. In this example, caffeine and palmitic acid levels in coffee were analyzed using GC with FID. Caffeine is smaller and less polar, so it is less attracted to the column and elutes first. Palmitic acid, which has a long alkane chain tail, elutes later due to a higher affinity with the stationary phase. Because peak dimensions are proportional to carbon mass, the concentration of each component can be determined from its respective peak area on the chromatograph and compared to standards of known concentration. The effect of column temperature was also explored. At 200 degrees, samples moved through the column twice as fast as the sample run at 180 degrees. Note that while peak heights change, the area under the curve remains constant. GC is an important technique for chemical analysis and is widely used in scientific, commercial, and industrial applications. Due to the simplicity of GC, chemists routinely use it to monitor chemical reactions and product purity. Reactions can be sampled over time to show product formation and reactant depletion. The chromatograph reveals product concentrations and also the presence of unintended or side products. GC is commonly used in tandem with mass spectrometry, called GC-MS, to unambiguously identify chemicals in samples or air. Mass spectrometry, or MS, separates molecules based on their mass-to-charge ratio and enables the determination of compound identities. GC-MS is a powerful tool, as GC first separates complex mixtures into individual components, and MS gives precise mass information and chemical identity. GC is routinely used in air monitoring to detect volatile organic compounds, or VOCs, which may arise from environmental pollution, pesticides, and explosives. GC can be used to track and identify VOCs both indoors for headspace analysis and outdoors for health, safety, and security. You've just watched Jove's introduction to gas chromatography with FID. You should now understand the basic principles of gas chromatography and FID detection. Thanks for watching.